Hey guys, today we're going to talk through a couple of circuit example problems. The first thing that I want to remind you about is just the basic way that we draw an electric circuit. So we have a battery and we have a wire that connects our battery to our components. In this simple circuit, I'm just going to draw one resistor, which is represented by that squiggly line. And then we're going to bring this wire back around to the positive terminal of our battery. Now, for this example problem, let's say that we have a 9.5 volt power source here, a battery, and we're connecting it to a 16 ohm resistor. And we want to know how much current is in this circuit. So in this problem, we know two things. We know that the voltage from the battery is 9.5 volts, and we know that the resistance from the resistor is 16 ohms. Okay, so the equation that we're going to use to solve this problem is Ohm's law, which is V equals I times R. In this relationship, we can identify how changing the voltage can change the current, or how changing the resistance can change the current, or if we need to up the voltage in order to increase the current because of an increase in resistance. Okay, so in this problem though, we are looking for current, which is represented by the letter I. So if we want to get I by itself, we need to move it to the other side of the equation. To do that, we need to get rid of the multiplication. To do that, we're going to do the opposite of multiplication, which is division. So we're going to divide both sides by the other term, in this case R. R cancels R, and when we rewrite our equation, we get I is equal to V divided by R. I flipped my equation around so that I have my unknown on the left side. Okay, so we can go ahead and plug in here. So I is equal to V over R, which in this case is going to be 9.5 volts divided by 16 ohms of resistance. If we grab a calculator, 9.5 divided by 16 is 0.593 amps. Let's go ahead and round that to the nearest hundredth place. So our answer would be 0.59 amps. Okay, let's do a little bit more complicated problem. Let's say that we have a circuit which is connected to a 16.5 volt power source, battery maybe. Let's say that it's got 3 resistors in it. This resistor has a resistance of 5.3 ohms. This resistor has a resistance of 6.8 ohms. And this top resistor up here has a resistance of, let's say, 10.1 ohms. Now, this is called a series circuit. And because this is a series circuit, we have some rules that are followed in series. First off, there's only one loop, so our current is going to be the same everywhere. Our resistance in total is going to be the sum of our individual resistors. And this 16.5 volts is going to be shared by each of these resistors, and the one that has the most resistance is going to have the most voltage. So we can write those 3 things as 3 equations, and these are the Kirchhoff rules in series. So total resistance is equal to R1 plus R2 plus R3. Total current is equal to the current through 1, which is equal to the current through 2, which is equal to the current through 3. And our total voltage is going to be the sum of the voltages through each component. Each of them is going to have just a little bit of the 16.5. So these are the Kirchhoff equations for a series circuit. You don't need to memorize these, they are on your engineering equation sheet. However, it's useful to understand what they mean. The one that you will use the most is this top one. The bottom 2 are mostly there for reference. So let's say for this circuit we want to know the total resistance, the total current, and the voltage used by resistor number 2. For total resistance, we're going to use that total resistance equation, R1 plus R2 plus R3. In this case, that's going to be 5.3 ohms plus 6.8 ohms plus 10.1 ohms. And if we plug that into a calculator, we get 22.2 ohms as the total resistance in that circuit. For the second one, we need to use Ohm's law. We know the total voltage from the battery, and we now know the total resistance. If we know the total resistance is 22.2 ohms, and we know the total voltage is 16.5 volts, we can use V equals IR, just like we did a moment ago, to find the unknown current. So if we do that, that means that I will be equal to V divided by R, just like we did in the first problem. That will be 16.5 volts divided by 22.2 ohms. And that gives me a total current of 0.743 amps, which if we round to the nearest hundredth is 0.74 amps. We're almost done. All right, so the last thing it asks us to find is the voltage through resistor number 2. Now, in a series circuit, the current is the same everywhere. So for this problem, I'm going to use Ohm's law, and when I use the voltage, I'm going to use the total voltage from, I'm going to use the total current that we just calculated, using the total current to find the voltage that's used just by this guy. In a series circuit, the current's the same everywhere. So that total current is used through each of these resistors. So for this third one, we're going to use Ohm's law again. This is going to be the resistor 2. I is the total current, and we're looking for V. So plugging in there, V is going to be I'm going to use the unrounded version, 0.743 amps, times the resistance of the second resistor, 6.8 ohms. And if we plug that in, we get 5.05 volts as our answer. Okay, let's do one more problem. So let's say instead of a simple circuit or a series circuit, we're looking at a parallel circuit. So let's say that I have a 9.5 volt battery connected to a 6.8 ohm resistor in one loop, a 7.6 ohm resistor in a second loop, and a 5.9 ohm resistor in a third loop. I don't know what the current is, but for this problem, we want to know the total resistance, the total current, and I want to know what the current through resistor number 2 is. For this example, we'll call this one R1, we'll call this one R2, and we'll call this one R3. Okay, so in parallel, our rules are a little bit different. In parallel, we have a resistance equation, which is derived from Kirchhoff's laws. We're not going to get into where it comes from today, but this is the equation. So the total resistance is equal to the inverse of resistor 1 resistance plus R2 to the negative 1, the inverse, plus R3 to the negative 1. And then we're going to take that sum to the negative 1. Again, we could talk about where that comes from today, but that's not the focus of the video. So this is the equation that we're going to use. We're just going to use it and move on for now. Our current in a parallel circuit is not the same everywhere. In this example, you can see that if we start at our negative terminal and we come to here, the electrons have a choice when they get to this junction, this branch, if you will. They can go up through this resistor or they can go over. So some of the electrons will go this way and some will keep going forward. Same thing happens when we get to this junction. Some of them will go up and some of them will go over. What happens ends up being that we get some of the current that goes through R1, some of it goes through R2, and some of it goes through R3. But at the end of the day, when they get back to that positive terminal, they add up to the total current. So our total current is going to be equal to I1 plus I2 plus I3. Now, our voltage in a parallel circuit is actually the same everywhere. Each of these has a direct connection to that negative and positive terminal, so they get the full voltage from the battery. So the voltage through loop 1 is equal to the voltage through loop 2, which is equal to the voltage through loop 3, which is equal to the total voltage from the battery. So if you remember in our series equations, these were actually backwards. In series, the current is the same everywhere, and in parallel, the voltage is the same everywhere. Okay, so let's go ahead and calculate this total resistance real quick. For this circuit, our total resistance is going to be total resistance equals 6.8 ohms to the negative 1 plus 7.6 ohms to the negative 1 plus 5.9 ohms to the negative 1, and we're going to take all of that to the negative 1. So, please make sure that you use a calculator to do this. It is a lot easier on a calculator. So, if we plug this in, 6.8 to the negative 1 plus 7.6 to the negative 1 plus 5.9 to the negative 1, and then we're going to take that sum to the negative 1 power one more time. Our total resistance in this circuit is 2.23 ohms. You can see that 2.23 is a lot less than the individual resistances of each of the loops of our circuit. And that's because the electricity has 3 different paths it can go. The overall resistance is much less than they would be individually. For the second part here, the total current, we're going to use Ohm's law again. V equals IR. And we're going to calculate I using the total voltage from the battery and the total resistance that we just calculated. So if we rearrange just like we did before, I equals V divided by R. Our total voltage from the battery is 9.5 volts. Our total current that we just calculated is 2.23 amps. So if we plug that in, we get a total current of 4.26, that should be ohms, 2.23 ohms. Our answer then would be 4.26 amps. So that's the total current for the entire thing. I'll go ahead and update my diagram over here and write 4.26 amps for the total current in my diagram. And for the last question, the current through loop number 2, we're going to use the exact same equation, I equals V over R, but this time it's going to be I2, resistor number 2, and the total voltage. Because resistor number 2 is getting the same total voltage from the battery according to our equations, but it's only getting a piece of the current. So if we plug in what we know here, the total voltage is 9.5 volts, R2 is 7.6 ohms, and I get that the current through that second branch is 1.25 amps. So it's getting about 1/4 of the total current. If I wanted to, I could also calculate the current through this one and the current through this one, and these 3 currents should add up to about 4.26 amps. That's a good way to check your work. Okay, let's do one that's even more difficult. Let's say we have a circuit. It's connected to a 20.5 volt battery. Let's say we have a resistor right here. This resistor has a resistance of 7.8 ohms, and it is connected to a parallel branch with two resistors like this. Let's say it's got 3 ohms of resistance on this side, and it's got 5 ohms of resistance on this side. For this circuit, I want to know the total resistance, the total current, and I want to know the current through resistor number 1, and I want to know the current through resistor number 3. Okay, first off, let's say this is R1, let's say this is R2, and let's say this is R3.
So this is a much more complicated circuit problem. In this example, we have the 7.8 ohm resistor, which is in series with a parallel branch of 2 resistors. So we will have to use our knowledge of Kirchhoff's rules to evaluate this problem. First, let's calculate the total resistance of the parallel loop. We can use our parallel resistance total resistance equation to do this. 3 to the negative 1 plus 5 to the negative 1, all to the negative 1. And that's going to give us our total resistance for the parallel branch. And the reason that we need that is the parallel branch is in series with our other resistor. So if we take our 1.875 ohms and we add it to the other resistor, we will in fact have the total resistance of the whole circuit, because the parallel branch is in series with the other resistor. So 7.8 ohms plus 1.875 ohms will give us our total resistance for this circuit. And if we round that number, our value will be 9.68 ohms. Now that we know the total resistance, we can find the next thing, which is the total current. And we can do that because we also know the total voltage of our circuit. So we can just use the Ohm's law equation. I equals V over R. So 20.5 volts divided by our total resistance of 9.68 ohms will give us our total current. The total current moving through all of the whole circuit is 2.12 amps. That means that the current through our first resistor is 2.12 amps. However, that is not the current moving through R2 and R3, because those are in parallel. So the 2.12 amps going into those two components is going to get split because they are in parallel. They will be sharing the 2.12 amps. So the first thing that we need to figure out next is how much voltage is moving through the first resistor. Because in series, the components are going to be sharing the voltage. So we need to figure out how much the first component is using to determine how much voltage is left for the parallel resistors. We can do this because we know the total current and we know the resistance of that first resistor. So 2.12 amps times 7.8 ohms will tell us how much of the voltage is being used in that first resistor. Once we know that that's how much voltage is being used by R1. If we subtract that from 20.5 volts, that will tell us how much of the voltage is left, and that's how much is being used by the parallel branch. That will be the current moving through the parallel branch, but it will still get split, so we need to determine how much of it is being used by R2 and how much of it is being used by R3. Fortunately, the math here is easy. We're going to use that total voltage to determine how much of the current is being split between our branches. So we're using the Ohm's law equation again. Our voltage divided by our resistance. The voltage here is how much is left from the 20.5. So if we plug in our numbers, we get that the voltage through resistor 2, or through resistor 3, is 0.792 amps. And if we plug in again, we could also get the same answer, or we can just take the difference. 2.12 amps minus our 0.792 amps is going to give us the current through resistor number 2. So there's multiple ways to solve that problem. So that was a harder problem. We'll talk about some more difficult ones in class. See you next time.